Hello. And hello, Computex. Are we having fun? Are we excited? I'm telling you now, Infineon Technologies, we are super excited. And why? Join us over the next 20 minutes, and we will give you an insight into this title, No AI Without Power. And of course, I know a lot of you in this audience recognize the revolution that is taking place with the exponential compute power requirements, which of course needs power. And from an Infineon perspective, we do not want to chase the markets. We wish to shape the markets with you, the customers, and of course our ecosystem. Now, I would like to now just test and calibrate you and see in the audience if you can get some of these questions right. Today, AI consumes equivalent of around 2 to 3% of the world's energy, and it's going to be growing significantly as seen behind. And on top of that, the GPU power, I mentioned this incredible growth of GPU. This is growing 10x per the indications behind us, and in fact, growing even further beyond that I'll show you later. And then, of course, we move on to the rack power. And here you can see that the rack power has exponentially grown again 10x for the forecasted projections. When I started, when I had hair, we were less than 30 kilowatts per rack. We will now be talking about collaborations up to 1 megawatt. And then this question. Let's understand, of course, every time we use such agents, the consumption of those 3 questions was equivalent to 1.5 times to 2 times charging your smartphone. So I think now you can understand where we are from the power requirements. In a data center, let's look at this data center here. 100,000 GPUs and beyond in a traditional data center. 100,000. And you can see us here building up all of the subcomponents of the data center. And you can see, of course, we go right the way from the switching racks, the power supply units, the backup supply units. And then you go into the compute tray. And again, there is lots and lots of power requirements going into powering the GPUs or TPUs, and then the smart NICs. Infineon, we're of course proud. We actually cover 100% of the power conversion steps. This to us is of course a key element that we wish to work with our ecosystem partners. Okay, so as I said, 100% coverage. And what do we mean by that in the power management areas? We mean the drivers, the switches, the power stages, the microcontrollers that are customized to make sure that they get the best out of the system. New families will also be launched. You can see here we go right the way through to modules, especially we'll talk about the 1 megawatt racks in a moment. And then on top of that, even sensors, magnetic sensors that we're providing into the data centers. Now, what I like to do is actually go into now a deep dive. And we will start in a very exciting area, and I know a number of our customers are in the audience around power supplies. And what we'd like to do is really just explain to you that over the last years, we Infineon have been developing latest technology, not just in silicon, but in silicon carbide as well as in gallium nitride to support the evolution of the topologies needed to power these racks. Now, these power supplies, anything, traditionally from 3 kilowatts up to the 3.3, you can do in a traditional, conventional way. As we move above the 5, getting to the 8, getting to the 12 kilowatts, that's where, of course, we need the latest technology coupled with the right topologies that we will be supporting with wide bandgap, namely silicon carbide and gallium nitride. And for your reference, and a little bit of a teaser, we're also developing 12 kilowatt three-phase solutions for the next architectures. And of course, these go up in scale as well. So as we work with the ecosystem partners, the power supply companies, we know that this is at the very beginning, and we are looking forward to bringing out this technology. Now, this is the next insight. This is a traditional AI rack server. You understand that we have the power delivery and backup area, and you have the IT payload. Overwhelming demonstrations here in Computex. This, again, without going into too much detail on this slide, is the standard topologies that are used. Here you take in the AC, you take it into the single phase, then of course you have the BBU, as well as the supercaps, and then you convert, let's say for example, down to 50 volts, and then you can do the IT tray conversion of the intermediate bus converters. All good. That makes sense. It's needed. But this will not get us to the future. What will get us to the future is what we've announced today. We actually have a collaboration with Nvidia, and we will be looking at the next architectures to support the 800 volt DC architecture. And of course, we have the IT payload, but the key thing is we're looking at a centralized ability to centralize the power delivery and the backup units. Now, this is going to be pretty groundbreaking. And at the end of the day, of course, why are we doing this? And why do we believe in it? And why are we now collaborating with Nvidia? This isn't about today. This is about as we move forward to the end of the decade. And we recognize, of course, the benefits not only in efficiency, not only in reliability, because you remove the needs for all of the separate PSUs, power supply units, you go centralized. You can also increase then ultimately the benefits of bringing that voltage, the 800 volts, in directly to the board. On top of that, the copper that is needed. And this scales. This scales to 1 megawatts and beyond. So, with this announcement, let me just take a few more moments to really show you how this is actually going to be used, as if I would call it the North Star. So first of all, you have the infrastructure, the medium voltage, whatever that 13 kilovolts, whatever it may be. That then, of course, will give you then the ability to convert the AC there into the DC, to create effectively the 800 volt backbone, down to zero. And then there, from the infrastructure area, you can have the long-term storage. And this is, of course, based upon effectively the standard capacitor technologies that are out there today, the electrolytics. Then from there, we will move that into the hall. And you then got a requirement for the medium energy storage, where you would use then, of course, the supercapacitors. Again, straight off that 800 volt rail. And then again, going now into the IT row, you have the ability to do the short-term storage, again on the standard electrolytic capacitors. Again, on the 800 volt. then the magic happens. Because you are bringing that voltage straight into the motherboard. And that's where you can convert the high voltage intermediate bus converters as well as the medium voltage intermediate bus converters, then back into core. And we recognized this as Infineon some time ago. And that's why we've been developing technologies like gallium nitride to make sure that we get the maximum ability to switch at higher switching frequencies to get the efficiencies as well as the densities. And we will be taking that 800 volt down to a nominal 54 volts, or we can, of course, bring that down to the 12 volts. And the same for the low voltage, as well as, of course, on the VRM. We can use the technologies of silicon as well as gallium nitride. So this, again, is the North Star. There's lots of topics that we need to be working on. We need to make sure it's protected. But again, moving away from the 54 volt rail, moving into this 800 volt, and of course going into the DC plane, we can then work on this to bring in the efficiencies, the reliabilities, and of course it will help overall the scaling factors as well. Now, that's good. But as we work within Nvidia, we have to also be somewhat realistic. And that's why we are saying, look, there is an intermediate step, a phased approach. And the first step there is on the IT payload. And then there will be a sidecar, of course, that will have the power delivery backup. So this will be the intermediate steps that we will be driving. And again, on the topology, I won't need to repeat it, but you can see here going in from the AC at the top, going in now all the way down to the sidecar, and then, of course, giving the compute rack the right level of density and efficiency that is needed. But again, we are super excited about moving to the end goal before the end of the decade. And we recognize Infineon, and we recognize Nvidia. We can't do it by ourselves. We need you, the ecosystem, the customer base, to come along this journey with us. And we will talk a little bit more about that later. Let's do the next deep dive. This is the intermediate bus converters. And again, this is the first power stage conversion. You have the high voltage IBC. These can be based upon the LLC topologies, where you can go to the 50 volt to the 12 volts, inductor, capacitor. That, I think, is also known. And then from there, we can do the medium voltage. And again, you can go down from the 12 volts, 6 volts, whatever is required. Now we're bringing something else new to the industry. And that something new is what we call an interleaved buck converter. You've heard it here for the first time. And why? Because we're going to be bringing this technology to market, and what we're going to be doing is using gallium nitride. And this is an example of the benefits of the 1.2 kilowatt base scalable solution. So first of all, look at that efficiency level. Look at the figure of merits. If you're in this space, I ask any of you now to look at this efficiency level and see how you can do it at the density that will be achieved with gallium nitride. And then, of course, the digital control. This will be giving us the advanced fault control. And then, as it says in the title, the subtitle, this is a modular approach. So we go to the 1.2. We can then, of course, scale this up to the 4, to the 8, to the 10, and beyond. The modular approach works with the interleaved topology. On top of this, we've got the transformerless as well, which brings lightweight, reliabilities. You can understand what this could bring for the industry. And then finally, that will reduce the switching losses. So we, again, are really excited about this area. Now, Another area that we wish to talk about is now the really exciting topic about how we are powering and teaming up with the world's leading GPU vendors on the planet Earth to make sure that we understand their requirements. And as you saw before, going from these 450 watts going up to now greater than 3,500 watts for the GPU. That is a challenge in power. But with that challenge, clearly brings these opportunities. And with that then, we would like to show you the next evolution of voltage regulator solutions. Let me talk you through this. You've got the GPU substrate motherboard. You can put then the components basically laterally next to the substrate. The next evolution will be the vertical power going underneath the substrate. We believe 8 to 10% system performance. This then ultimately will move into substrate integration for vertical power. Again, another step increase of a system efficiency. Ladies and gentlemen, what we have on this slide, this is not fiction. This is reality. This is us as an industry, and especially here with Infineon Technologies, working with the leading GPU vendors to make sure that we understand not just next generation, but N+2, so we can provide the requirements on the power management to achieve the ultimate goals. Now, I'm sure a lot of you are saying, well, how's this done? Where are we? Let me just walk you through a little bit of a journey on these power stages and these module solutions. So we started way back in 2011. We got 0.4 millimeter squared performance amps, millimeter squared amps. And then from there, we started to develop an ecosystem around chip embedding. That's not easy. We had to go and find partners in the industry that could do chip embedding, and of course, at these current and power levels. We then created that, which went from 0.6. Then we went to 1 amp per millimeter squared, and then the journey continues as we bring out the family of modules, 1.5 and then 2 amp per millimeter squared. Now, one thing you will notice, it took us a decade to go from the module over module solution to then effectively going into the chip embedding. But effectively, since 2024 until now, we've 2x'd the amp per millimeter squared. And that's not where we stop. Per the video that you have just seen, we will be going above the 3 amp, and of course, we'll be going eventually above the 4 amp per millimeter squared in our labs as we speak. Now, saying that, all of these have to hit certain fit form functions, height, density, performances. So that is a topic that we are looking forward to bringing out the leading edge solutions for VRM. And of course, what does this mean? This means energy efficiency between the 8 and 10%. And I would say, and beyond. It also improves the power density between 30 and a staggering 60%. And then ultimately, on top of that, the best-in-class robustness as well as reliability. We take that incredibly seriously. Maybe it's a bit of the German DNA of Infineon. Maybe it's our heritage of automotive and industrial. But we will not compromise on quality. And we understand the downtime and the reliability needs in these data center and these racks, the uptime. And that is something that we are very, very cautious of and making sure is the front of all of the designs that we do. And on top of that, Infineon, we're proud here because we recognize that if we use today in the data centers that are installed the latest technology, we can save a staggering 22 million metric tons of CO2. In simple language, that's equivalent to 7.5 million combustion vehicles. And that's where we are today. Can you imagine what it's going to be like moving forward? 48 terawatts an hour you can save using Infineon technology. That's equivalent of all the electricity that is used today in Portugal. And then from there, we also understand we have to have best-in-class total cost of ownership. All of that other technology and innovation, we wish, of course, to address these two key points. So you can see we are super excited. First of all, in summary, we recognize that this innovation and collaboration with Nvidia will take us to this North Star for the future power distribution for data centers, accelerating compute power. On top of that, we're not going to be able to do it, we believe, as an industry, just with silicon. Wide bandgap materials will be required. Whether it's on the silicon carbide for high voltage modules, as we go in from the MV, the 13 kilovolts, going into the 800 volt solution, or moving forward as we switch higher frequencies to support density and efficiency with the gallium nitride. And it wasn't so long ago, gallium nitride was, yeah, okay. We've also launched the world's first 12-inch gallium nitride wafer. We're moving to 12-inch on GaN. This will be required to support the demand that we see how GaN will be so disruptive. And on top of that, on the silicon, we have teams today walking around Computex. They're not just working on the next generation silicon solutions for AI. They're not just working on the second generations. They're working on the third generations already. Because we recognize that silicon will also have a strong play. And then, of course, the total cost of ownership. And my last sentence here, if anybody's following Infineon, we have this responsibility of not only driving digitalization, but also decarbonization. Thank you very much.